Hello everyone, let me introduce myself. My name is Putri B. SAFITRI and you can call me Putri. I was graduate from ITB University and then I continue my study to the University of Edinburgh, majoring in Medicinal and Biological Chemistry. And I've got the scholarship from FPDP or from the government. And I've just finished my study in August, so it's like a month ago. And I have a big passion in teaching. I can teach science and math, especially chemistry. And I think that's all about myself before we go to the topic that we're going to discuss today. Hello everyone, so today we're going to discuss about enthalpy changes. But before we jump to the topic, we have to know about the endothermic and exothermic reaction. What is exothermic reaction? Do you know about it? Okay, let's discuss together. The reaction called exothermic if the heat energy is released to the surrounding, and as the result, the temperature of the surrounding increases. So that's it, the exothermic reaction. So for the example, if you react magnesium with the sulfuric acid in the test tube, you will feel the test tube becomes warmer, and it indicates the temperature of the surrounding, or in this case, the test tube is increases. So that's called exothermic reaction. Okay, I'm gonna write the example. Okay, so this reaction will release the energy, so the test tube will become warmer. And that's about exothermic reaction. It's easy to understand, right? Okay, so now we're gonna discuss about endothermic reaction. On the contrary, if the energy is absorbed from the surrounding, it's called endothermic reaction. And as the result, the temperature of the surrounding is decreases, or it's become colder. Okay, the example is if you react ammonium chloride in the water, you can feel the test tube become cold, and it indicates the temperature of the surrounding or the test tube is decreases. So that's called endothermic reaction. Okay, I'm gonna write the example. Okay, that's all about exothermic and endothermic reaction. Now let's go back to enthalpy changes. Okay, so what is it? Enthalpy. Okay, enthalpy simply is the total energy that associates with the material that react in the chemical reaction. Let's go back to enthalpy changes. So what is it enthalpy? Okay, let's find out. Enthalpy, it's simply defined by the total energy that associated with the material in chemical reaction. So that is the definition about enthalpy. It's quite simple. However, we can measure the enthalpy, but we can measure the enthalpy changes. So what is it, enthalpy changes? Okay, let's find out together. Enthalpy changes is the exchange of energy, okay, between chemical reaction and its surrounding. And you have to remember that this exchange of energy must be at the constant pressure, because when the pressure is different, the energy that absorbed or the energy that released will be different. Okay, and that's the definition of the enthalpy and the enthalpy changes. Now, the enthalpy changes can be calculated or can be measured by this simple formula. Delta H equals to enthalpy of the product minus enthalpy of reactants. Okay, now I'm gonna tell you about this symbol. So, the enthalpy changes has the symbol delta H. This is for enthalpy changes. And the unit for the enthalpy changes is kilojoule per mole. Kilojoule per mole. Or you can also write kilojoule mole to the power of -1, like this. And this H, it means just enthalpy. Okay, that's how we can calculate the enthalpy changes. Okay, so using this formula to make you more understand about enthalpy changes, we can draw the enthalpy changes or the reaction pathway of a diagram. So let's draw the reaction pathway diagram. And please note that the reaction pathway diagram for the exothermic and endothermic reaction is different. How is it different? Okay, let's see together. So this is the X line for reaction pathway, and this is the X line is for enthalpy. Same right here. This is reaction pathway, and this is enthalpy. Don't forget, the unit is kilojoule per mole. So for the exothermic reaction, so I am going to write this one exothermic, while this one is for endothermic. Okay, for the exothermic reaction, you can write right here and right here. And this is for enthalpy of a reactant. I'm going to just write R for the reactant. And this one, enthalpy of product, or just P. Can make the dotted line and like this. Okay, and the main line. Okay, so this is the exothermic. We can add, this is for the reactant. There's something here called EA, or activation energy. Right here, it's for enthalpy changes. And this is for the product. This is for exothermic reaction. And how about endothermic reaction? Okay, it's a bit different. This is for enthalpy for product, and this one, enthalpy for reactant. Okay, we're gonna make dash line, like, and dash line, and the main line, okay, from here, it should be right here. And we're gonna write this as reactant, and this is for product, and there is an arrow here for EA, delta H. So this is the difference between a reaction pathway for exothermic and endothermic reaction. You can see that for the exothermic reaction, delta H for reactant is bigger than delta H for the product. Meanwhile, for endothermic reactions, delta H for product is bigger than delta H for reactant, because in the endothermic reaction, the reaction will absorb the energy. So you can see that the energy, the arrow is going up because the energy is absorbed. It means the energy is bigger. Meanwhile, for the exothermic reaction, the energy is released. So the arrow is going down because the energy is released. And if we go back to this formula, delta H equals to the delta H products minus delta H reactant. If the result is negative, that means the reaction is exothermic reaction. Meanwhile, if the result is positive, the reaction is endothermic reaction. Let's compare this result and this diagram. Negative, that means the reactant is bigger. So this is reactant, the enthalpy is bigger than the product. So the result will be negative. So this is exothermic reaction. And for this one, the enthalpy of product is bigger. So the result will be positive. So this is diagram for the reaction pathway. The reaction is endothermic. Okay, so that's about the diagram for the reaction pathway between exothermic and endothermic reaction. So it's quite easy to understand, right? Now you can define the enthalpy and enthalpy changes. Also, you can draw the reaction pathway diagram. Okay, now let's move on. Okay, now let's move on to type of enthalpy changes. Okay, firstly, we have to understand what's the meaning of standard enthalpy changes. Okay, so I'm gonna write this standard enthalpy changes. Okay, it's a little bit different with enthalpy changes because when the standard enthalpy changes means the reaction is under standard condition. So, what is standard condition? Okay, there are at least 2 points for the standard condition. Firstly, pressure of 101 kPa kilopascal or 1 atm, and then second one, the temperature of 298 Kelvin or 25 degrees Celsius. So this standard condition is for the standard enthalpy changes. Okay, so let's go back to the type of enthalpy changes. based on the type of the reaction taking place, we can divide the standard enthalpy into at least 4 different enthalpy changes. So based on the type of the reaction taking place, we can divide it. One, standard enthalpy changes of formation, and then the second one is standard enthalpy changes of combustion, okay, and the third one, standard enthalpy changes of neutralization, or the common form or general form is the standard enthalpy changes of reaction. Okay, this is at least the 4th type of standard enthalpy changes. Let's discuss one by one. Okay, the first one is the most common one, standard enthalpy changes of reaction. So, what's the difference of the symbol between these enthalpy changes and the standard enthalpy changes? So, the standard enthalpy changes, okay, symbol, there is this little symbol for the standard enthalpy changes. We can read it as delta H reaction standard, or you can also read it as delta H reaction note, like something about that, like note. Okay, so this is the symbol for the standard enthalpy changes of reaction. And what is the definition of standard enthalpy changes of reaction? It simply is enthalpy changes when the reactant react to form the product. Okay, and remember, because is the standard enthalpy, we must add under standard condition. Okay, that's the definition of standard enthalpy changes of reaction. And what is the example? Okay, I'm gonna give you the example. The simple example, just like the formation of water, hydrogen plus oxygen from water. Okay, and this is the example for the enthalpy changes of reaction. And the delta H is minus 286 kilojoule per mole. It means the formation of water release the energy of 286 kilojoule per mole, and this is 1 mole. How about if we got like 2 mole of hydrogen? For the example, 2H2 plus O2 and 2 mole of water. Since it's 1 and it's 2, the delta H also multiply by 2. So the delta H reaction, okay, equal to 572 kilojoule per mole. Okay, so if we got like a half mole of water, then the enthalpy is divided by 2. Okay, so it depends on the mole of the product we obtain. Okay, so that's the standard enthalpy changes of reaction. Okay, and the second one, standard enthalpy of formation. Okay, so the symbol, it's simply delta H. You can add this F and standard. Okay, and the definition is the enthalpy changes when a compound is formed from its element. And don't forget, we should add under standard condition. So just like its name, this enthalpy of formation, it's like when a compound is formed from its element under standard condition. And what is the example? Okay, let's look at the example. Okay, the example is the formation of ferric react with oxygen to make this compound. Okay, this is the example of the standard enthalpy of formation, and the standard enthalpy for this O3 is minus A2 4.2 kilojoule per mole. Okay, let's jump to the third example, or to the third type of enthalpy changes. Standard enthalpy changes of combustion. Okay, the symbol for this standard enthalpy changes is symbol. You can simply add the C right here, and don't forget the symbol for the standard. And the definition of the standard enthalpy changes of combustion is the enthalpy changes when a substance is burned in the excess of oxygen, and don't forget to add under standard condition. Okay. So you have to remember that the combustion always involves this object. So the example of this reaction, okay, the example is the combustion of methane gas. Okay, so this always involves this oxygen. If you find the reaction that contains oxygen, that means it's combustion. And the enthalpy standard for for this reaction is minus 830.3 kilojoule per mole. Okay, and this is the third type, is the enthalpy changes of combustion. And the last type, the fourth type is standard enthalpy changes of neutralization. Okay, and the symbol, it's similar, of course. Symbol is delta H. You can add this neutral. Okay, and this is for the enthalpy standard. And what is the definition? Just like its name, neutralization, which means you react the acid and the alkali and you form the water. So the definition is the enthalpy changes when 1 mole of acid react with one. Okay, I'm just gonna write this: an acid react with an alkali to form water. So let's find the very simple example. When you react hydrochloric acid with sodium hydroxide, you'll obtain water and sodium chloride as the salt. And enthalpy changes for this reaction is minus 57.1 kilojoule per mole. Okay, I almost forget to add that we can add like this: delta H. We can make the square bracket with CH4. So if we go back to this example, look at this one. And this one, in the bracket is the reactant because it's combustion, so the reactant will burn. This means this enthalpy for the reactant. That's why it's the reactant in the bracket. While this one, the component in the bracket is this one, the product, because this is the enthalpy of formation. So this is the delta H for the product, the formation of the product. So that's the difference between combustion and formation. Okay, so that's 4 types of enthalpy changes. I think it's quite easy to understand. So now you understand about enthalpy and endothermic and exothermic reaction. We've learned about how to draw a reaction pathway diagram, and we also learned about the type of enthalpy changes. Okay, let's move on to the next topic. Okay, next we're gonna talk about how to calculate enthalpy changes. There are at least 2 ways to calculate enthalpy changes. So the first one is using Hess law, and the second one using bond energy. Okay, let's discuss one by one. Okay, firstly, the Hess law. Okay, to make you understand about the Hess law, I'm gonna draw the Hess cycle. Okay, so the reactant, the product, and Y. So the first one, we have direct route. Okay, this is direct route. So from the reactants directly react to obtain the product. So we call direct route. And there are also this one. So before it creates the product, there are 2 intermediates, F and G, from the product, and we call this indirect route. Okay. And there are also the third one. So there are 2 steps of the intermediates. So we call this indirect route. Indirect route. Okay, so this is the direct route where the reactant directly react to form the product, and then there are also indirect route where the intermediate is formed to finally form the product, and also there is the reactant and then form the first intermediate and then form the second intermediate before finally the product is formed. And the Hess law stated that both direct and indirect route will give the delta H value the same, no matter how many steps in the indirect route. So instead, it Hess law, the enthalpy changes of both direct and indirect route are the same. No matter what, no matter how many steps are in indirect. So if I say this is delta HR, and this is delta H1, and this is delta H2, it will be the same. So like delta HR equals to delta H1 equals to delta H2. Okay, this is the Hess law. Okay, so I'm gonna make another Hess cycle to make you more understand about this. So we have this reactant and the product and this element. Okay, there is direct route. This is delta HR and this is delta H2, delta H1. Okay, here we have direct route. This one from the element to the product. It's directly from the product, and we have this indirect route. Okay, so from this diagram, we can make the formula delta H2, since it's direct route, equals to delta H1 plus delta H reaction. So delta H reaction equal to delta H2 minus delta H1. Okay, this is formula, and we can use this formula to calculate the enthalpy changes of reaction from the enthalpy changes of formation. formation. So remember the difference between this formation and we have another one, combustion. So what if we have the data of the enthalpy changes of combustion? Of course, the formula is a little bit different. Okay, so yeah, I'm gonna make you the diagram. Element plus oxygen, and this is the compound plus oxygen, and there is a combustion product. Okay, we're gonna make this box. Okay, so we have this one direct route from the element directly from the combustion product, while this one is indirect route because we have to make the compound and then we have to make a combustion product. So this is indirect, and this is direct. And if we write this one, this is delta H of formation. Remember, from the element to the compound is formation, and then from this one delta H2 and this one delta H1. So from this diagram, we can take the formula delta H reaction equals to delta H formation equal to delta H1 minus by delta H2, because this is the direct and this is the indirect. Okay, I'm gonna make a box for this. So if this diagram used to calculate the enthalpy changes of reaction from the enthalpy changes of formation, this one is from the to calculate the enthalpy changes of formation, okay, formation from the enthalpy changes of combustion. Okay, so remember that the formation and the combustion is different. Well, the formation is the enthalpy of the product, while the combustion is the enthalpy of the compound that will be burned with the oxygen. Okay, so if you have the data of the enthalpy changes of combustion, then you can use this formula, this one. Meanwhile, if you have the data of the enthalpy changes of formation, you can use this formula. Okay, so this is the first way to calculate the enthalpy changes. Okay, next is the enthalpy changes using bond energy. Okay, now we go to the second way to calculate enthalpy changes. It is bond energies. Okay, second way, bond energies. So the enthalpy changes caused by bond breakings and forming. And bond breaking, it requires the energy. It absorbs the energy. So we can say that this is, remember, absorb the energy and the term. And meanwhile, this bond formation is release the energy. Or we can say that as exothermic. Okay, so it's quite easy to remember that absorb is endothermic and release is exothermic. And if the energy required to break the bond is less than the energy released, to form new bonds. Okay, so this rate to break the energy less than the energy released to form new bonds. That means the reaction will release the energy. So if the reaction releases the energy, we can call it as the exothermic reaction. So on the contrary, if the energy to break the bond more, okay, you have to remember this one, more than the energy released to form new bond. This means the reaction will absorb the energy, or the energy will be absorbed. And absorbing the energy means the reaction is endothermic. Okay, so this is the quiet concept about the bond's energy. And now, how do we calculate the enthalpy changes by the bond's energy? Okay, it's just a simple formula. Okay, we can use this formula. Delta H equals to delta H for bond broken minus delta H for bond forming. Okay, this is the formula to calculate the enthalpy changes. Okay, that's the two ways to calculate the enthalpy changes. So today we've discussed about endothermic and exothermic reaction, enthalpy and enthalpy changes, the type of enthalpy, and also how to calculate the enthalpy changes. Okay, so it's all about the topic of enthalpy changes. And this is the end of the discussion for today. But don't worry, to make you more understand about this topic, we're going to discuss some exercise related to this topic. Okay, let's start with the question number 1. Okay, the question is, draw the full reaction pathway diagrams including activation energy for A, the combustion of sulfur to form a sulfur dioxide in exothermic conditions. So we've learned about how to draw the reaction pathway, so we can do it together. Okay, let's do it. Firstly, we need to draw this line X for the enthalpy, and then forget the unit, kilojoule per mole. Okay, and then this y-axis is for reaction pathway. Reaction pathway. Okay, so this is the reaction between sulfur and oxygen to form sulfur dioxide, SO2. And remember, this is the exothermic reaction, which means the reactant should be up here and the product should be up here, should be down here. So this is the enthalpy for the reactants. I am gonna just write this R, and this is the enthalpy for the product. This is P. Okay, and we can make the dash line right here, okay, and right here. Okay, now we make the true lines for this. Okay, after we got the line, we can add the reactants right here, S plus O2, and we can also add the compound form right here, SO2. Okay, and remember we have to draw the arrow for the activation energy, and you have to remember to draw the arrow. It starts from this, the enthalpy for the reactant. The arrow starts from this, go up here until the top of the diagram, and we can name it EA. Okay, and then the other arrow go down right here. This is for the enthalpy of formation. Okay, so this is the diagram. This is the answer of the question number 1 and question A. So I think this is quite easy, right? It's similar to the example. Okay, so we can jump to the next question, question B. It's similar. Question B, we have to draw the endothermic reaction of water. You can write the phase here with graphite or carbon, the solid condition, solid phase, to form hydrogen and also carbon monoxide. Okay, so this reaction is endothermic, and it means the diagram will be different with this one. Okay, so the first one we have to draw this line. Okay, and this is for the reaction pathway, and this line is for enthalpy, and you have to remember the unit is kilojoule mole. Okay. Since this endothermic reaction, which means we have the reactants here, down here, delta H for the reactants, and this one up here, delta H for the product. So it's different, right, between endothermic and exothermic. And we can draw the dashed line here to help us draw the line. Okay, and then can draw the line. Remember to draw the line from the reactant. So from this, go up here and end it here. Okay, so we can write down the reactant right here. So the reactant is this one, water plus carbon, and the product is hydrogen gas with carbon monoxide. And also remember to write the activation energy arrow. And activation energy arrow start from the reactant. Okay, so from down here, go up here until the top. Yep, and we can use it. Activation energy. And we can also draw the arrow from here to top here. Okay, this is for delta H formation or the enthalpy. Okay, so this is the answer for the question number 1, A and B. This is the difference between the reaction pathway diagram for the exothermic and endothermic reaction. Okay, so I think it's quite easy, you guys. I'm sure you can do it alone. Now let's do the question number 2. Okay. The question is draw the enthalpy cycle for the reaction of aluminum with ferric trioxide to form Fa and aluminum trioxide. So we can start to remember for the reaction, the cycle of the Hess or Hess cycle. We can write the reactant right here. So this is the reactant to Al, and the phase is solid plus. Okay, we can draw here for the reactants, and then we can draw the product right here. Okay, solid plus aluminum trioxide, and we have this arrow. What is it called? Okay, because this is the reaction, enthalpy of the reaction, so we call this arrow delta HR. Don't forget the standard. Okay, standard. And for this Hess cycle for the reaction, we have this right here for the element, and we can identify each element. What we have right here? We have aluminum right here, Al. Also we have ferric. Also we have this one, oxygen, and we can balance the reaction, Al and then Fa and more of oxygen. And the next step is to draw the arrow. Okay, so right here and right here. So you can then draw or write down the enthalpy right here, delta H. You can look at this. This is the product. You can say that this is the product from this reaction. This is the product. So this is the enthalpy changes of this one. And then when we see this arrow, there is the product here. Okay, this is the product. Okay, so this is the enthalpy changes, delta H F. Okay, don't forget the standard for this one. Okay, so this is the answer for the question number 2 on A, and this is the question number 2 B. Okay, so it's a bit different with this one because this is like the combustion reaction. So we have to draw the Hess cycle for the formation of ethanol. Okay, you have to remember that ethanol is C2H5OH. Okay, and then using the enthalpy changes of combustion. Okay, so we have to know this is the combustion and this is the formation, so it's a bit different. And if this combustion, we have to add oxygen. Okay, so we can write down this element here. What is the element we have right here? We have carbon, and then we have hydrogen, and then we have oxygen. And then we can make a box here, and the product right here, the compound, we have ethanol, and of course we have to add the oxygen. Okay, and then the product of the combustion reaction, you have to remember the product of the combustion reaction is always carbon dioxide plus water. Okay, so now let's balance this reaction. Okay, so this is 2C and H3. Okay, and then this is O, 1 half O2, and CO2, we have 2 CO2 and 3 waters. Okay, and then we draw the arrow. So this, you can see that this from the element, and then we have a compound, so this means this is delta HF because this is the formation. While this one and this one, the arrow go down here. So this is the product of combustion, and this is will burn with the presence of the oxygen. So we have this delta H combustion. Okay, of ethanol. This is 5OH. Okay, and for this one, it's also will react with oxygen. So we have delta H combustion standard for. Remember, we have to atom here C and delta H for hydrogen. So this is the Hess cycle for the formation of ethanol using enthalpy changes of combustion. Okay, that's for number 2. Okay, now let's do the question number 3. So the question asks to calculate the enthalpy changes from this reaction, and we provided by this data of the enthalpy changes formation of each compound. So that means we can do this calculation using the Hess law. Okay, so let's just write down the reaction here. Okay, we have natrium hydrogen carbonate. Okay, we have this reaction. And now we can calculate the enthalpy changes using Hess law. Actually, you can calculate the enthalpy changes by firstly drawing the Hess cycle. But I can tell you the easiest way to do this calculation. You can just use this simple formula. Okay, delta H equals to delta H of the product minus delta H reactants. Okay, so you can use this formula to calculate these enthalpy changes of this reaction. But remember, this formula can be used if you have this data, okay? The data of the enthalpy changes formation of each compound. So we can do now the enthalpy changes equals to, we have the product, these 3 compounds, and also we have this reactant, 1 compound. But you have to consider this number. Okay, you have to consider this number, the number 2, which means you have to times the enthalpy by 2. Okay, so let's see the enthalpy of the reactant product first. So this is the enthalpy changes of formation standard of this compound. So we can write down sodium carbonate plus delta HF standard for this compound, carbon dioxide plus this enthalpy changes for this compound, delta HF for water minus by, okay, since we have this number 2, we have to calculate this by 2. Calculate this 2 times delta HF standard for sodium hydrogen. This is the formula. Now we can substitute the number. So we have this data from here. We can just write down right here minus 1130, okay, 0.7 plus by this delta HF or this carbon dioxide, you can see right here, and then plus this delta HF for this water, you can also see right there, minus, don't forget the minus if you have that minus, and then minus, okay, you have to remember there's 2 times the enthalpy changes for the this one, sodium hydrogen carbonate, times by 2, so this is, okay, now we can just calculate this one, this plus by this, and then plus by this, and then minus this. Okay, so we have this number, it's minus 181.0 minus, and we have minus right here. Okay, minus and minus mean we have plus. Okay, and the result is plus 91.6. And don't forget the units for the enthalpy changes is kilojoule per mole. Okay, so this is the result. The result is positive, which means if we have the positive number, the reaction is endothermic. So this is the answer for the question number 3. Actually, you can use the Hess cycle. So firstly, you can draw the Hess cycle, and then you can use the formula using delta HR equals to delta H2 minus delta H1, and then you can substitute the number from this data, but you can also use this formula. But if you think that this formula is easier, because I think this is easier compared to you have to draw the Hess cycle first, you can use this formula and the result will be the same. 91.6 kilojoule per mole, and the reaction is endothermic. Okay, so that's for the question number 3.
Okay guys, now let's do the question number 4. Okay, so for the question number 4, it's still the same that we asked to calculate the enthalpy changes for this reaction. However, if we look at this data, we have this energy data or bond energies data. So we can't use the Hess law, but we can use the bonds energy technique to calculate these enthalpy changes. So now let's do write the reaction. So we have hydrogen here plus iodium to create hydrogen iodide. And my suggestion is to make this reaction style like this, because we're gonna calculate the bonds energy, so we have to make sure that the bond is visible. So like this, we have this bond and we have this bond, and also for the product we have this bond. And you have to consider this number. If we have like number 2, so you must times the energy by 2. But if this number is 3, then you must times the energy bonds to 3. So after we found out each bond, we can just use this to make it easier. Delta H for bond broken. Delta H for bond broken, that means this compound and this compound, and delta H for bond formation. So okay, and for the bond broken, we have this one times by H bond, and then we have 1 times I bond. And for this bond formation, we have 2, remember, 2 times HI bonds. Okay, and now we can substitute the numbers. For this HH bond, the energy is, you can look at here, okay, 436 kilojoule per mole. And then for I bond, you have the number like 151 kilojoule per mole. And for this one, 2 times by, okay, 299. Okay, and remember, if you have the negative value for this one, then you have include the negative, but since this all positive, you can add positive number. Okay, so you can just calculate this, the total. We have this total and this total. Okay, so we just 436 plus 151, it means 785. And then for this one, 2 times 295, okay, I mean 29, it's 8. Okay, so this is 59, oh, this is 9, 598. Okay, so we have this delta H for bond broken, and we have delta H for bond formation. And for delta HR, we can just simply use delta H bond broken minus delta H bond formation. So we can just substitute this number 5 at 7 minus by this number 5, 9, 11. So the result is positive, I mean a negative 11. Don't forget the unit, kilojoule per mole. And if you remember correctly, this negative sign means the reaction is, exothermic reaction. Okay, so this is the answer for question number 4. So it's still about the calculating of the enthalpy changes, but now we have tried to use the energy bonds calculation. But it's still easy because you can just substitute the number from the energy bonds. And don't forget, if you have this coefficient, not only 2, you can the coefficient like 3, 4, or 5, you can just times this coefficient by the bonds energy, and then you can calculate this by this formula and you get the number. Okay, so that's quite easy, right? So let's move to the next question. Now let's do the question number 5. Okay, for the question number 5, as you can see from this question, we still have the same question like number 4, but it's a little bit complicated. If you look at this reaction, it's more like a bigger compound than the first one. So we can start by write down the equation reaction. So we can remember to write down like this. Okay, and we have this O H H H H H H, okay, plus 4O2, okay, to form the product CO2 and 3CO2 and water. Okay, now we have this equation reaction. Now we can identify each bond. So firstly, we have to identify, okay, we use this delta H for bond broken. Okay, and this one, delta H for bond formation. Okay, for bond broken, we have to look at this. Okay, this one, this is for bond broken. First, CH bond. How many CH bonds? Let's calculate. We have 1 CH bond and 2 CH bond, 3 CH bond, 4, 5, and 6. So we're gonna write right here 6 times CH bond. Okay, and then we're gonna calculate CC bond. Okay, now we have 1 and 2 CC bond. So we're gonna write 2 times CC bonds. Okay, and the next we have let's use this color, CO double bond. And we only have like here 1 CO double bond. So it's just 1 times CO double bond. And lastly, we have this oxygen double bond. But don't forget, even if just 1, you have to consider this number. So it is like 4 times oxygen double bond. So we have identified all this bond for the bond broken, and now let's identify the bond for bond formation. So first we have this CO double bond. How much the bond we have? 1, 2. Okay, but not only 2, because remember this number, we have to times 2 by 3, so it's like 6 times double bond CO, and then the last bond we have is this one, OH bond, and we have 2 bond, but we have this number, so 2 times 3, 6, so this is 6 times HO bond. Okay, so now we have identified all the bonds we have in this reaction. Now we can just calculate the bond broken and the bond formation energy. So this is CH bond, we have the number 6 times positive, 4, 1, 3, and this one 2 times. For the CC bond we have 3, 4, 7, and for CO bond we have times 1 times 8, 0, 5, and for O double bond we have 4, 9, 6. Okay, and then we have this bond, CO bond, we have the energy bond, 6 times this one, and for the last bond we have 6 times OH bond, which is 4, 6, 5. Okay, now we calculate all the bond. Okay, this total and this total. Okay, if you calculate this bond, we have this number 5961, and this is 7620. Okay, so for calculating the enthalpy changes, we can use the same formula. So delta H equals to delta H for bond broken minus delta H for bond formation. Okay, formation, and we just substitute this number 5961 minus 7620 equals to negative, okay, don't forget because it's negative, 1659, and the unit is kilojoule per mole. And now we've got the value of this enthalpy changes, and the value is negative, which means the reaction is right, exothermic reaction. Okay, now we have finished all the exercise for this topic. We cover all the subtopic, and I think it's not that hard, and I hope you can do it alone as well. And thank you for discussing this material with me. See you next time.